All right, in this video we are going to talk about energy. We were talking about energy in the last video. We're going to talk about the relationship between energy and Q. This should probably also say and the equilibrium constant. If you remember, the equilibrium constant is just a special case of Q. Q is called the reaction quotient. So if I have some pretend reaction, little a, a certain number of moles, that's what the little a is, of molecule A, big A, turns into a certain number of moles, which I'm going to call B, of molecule big B. The reaction quotient is just the concentration of B to the little b power divided by the concentration of A to the little a power at any point in time for the chemical reaction. This does not have to be, it's the same formula as the equilibrium constant, but when you calculate this for the equilibrium constant, the concentrations of A and B have to be at equilibrium. If you're calculating Q, the concentrations of A and B don't have to be at equilibrium. They can be at any point in time for the chemical reaction. So that's just a refresher on what Q is. We are going to talk about something called G, which stands for a person's name. Gibbs is the dead guy's name. He was a famous chemist who worked at Yale. And we are going to talk about something called Gibbs free energy. And Gibbs free energy, or just free energy, is the energy that a molecule or a bunch of molecules have that can be used to do work. And what I mean by work is the ability to push or pull or move other things around. Just generally speaking, you should just think of this as how much energy a molecule or collection of molecules have, or you can think of it in terms of chemical reaction, how much energy a chemical reaction has at a certain point in time, at a certain snapshot, to be able to do work. So here is a very simple chart. On the y-axis is the amount of Gibbs free energy that a molecule has, and here's my pretend reaction. A turns into B, B can turn back into A, and you can see that in my pretend reaction A has more energy than B. What you say in this case when A has more energy than B is that if you want to calculate the change in free energy in this reaction, change in free energy, so that's going to be written with the Greek letter delta and a G, is equal to the free energy of B minus the free energy of A. And this is always how you do it. You always do the stuff that you end up with, the final stuff, minus the stuff that you started with. The other thing that I want to point out is that it's pretty much impossible to measure the absolute free energy that a molecule has. What chemists and biologists and people who do these kinds of things do is they measure the change in free energy. So they measure this delta G. You will hardly ever see, certainly not in this course, you won't see just absolute numbers for free energy of a molecule. You'll always see this number, the change in free energy when something is converted into something else. I want to talk about this specific situation again. What we know is that B is a lower number, whatever it is, than what A is. So if this is a small number, and this is a bigger number, you can already tell that if you take a small number and subtract away a bigger number, you are going to get a negative number. So whenever the end stuff that you have has less energy than the beginning stuff that you have, the delta G will be less than 0. And this has a special significance, or there's a special term associated with this. When you have a forward reaction where the delta G is less than 0, you say that the forward reaction is spontaneous. What that basically means is you don't have to add any extra energy to this reaction to have it move in the forward direction. And you should know this. In a lot of the rest of this course, we are going to talk about the delta G of reactions, the change in free energy that a reaction might have or that we can calculate. And there are a bunch of different ways of calculating this, and I'm going to drop a couple of equations on you in a little bit. But right now what I want you to know is that if you have a chemical reaction where the delta G is a negative number, where it's less than 0, that means the forward reaction is spontaneous. Now, delta G is change in free energy for a reaction, and so I just want to talk about the units of delta G. The units of delta G are always some energy unit divided by moles of reactant, let's say. So if I have A turns into B, and I calculated the delta G for that reaction, it would be some energy unit. You could do it in a number of ways. You could say it's some energy unit per A molecule, but then you're going to get really tiny numbers. Usually it's written as per mole of reactant. So if I showed you the delta G for this pretend reaction, it might be joules per mole, or it might be kilojoules per mole, or calories or kilocalories. It'll be some energy unit, usually divided by per mole of stuff that you have in your reaction. So this is just to get you accustomed to the units that you're going to see. Another thing that I want to point out is that imagine we have this situation. This is a spontaneous forward reaction. Imagine that we have our test tube and it's filled with A's, no B's. The delta G for the reaction under this situation is going to be negative because I've got all these high energy things. They can, at least some of them are going to turn into these lower energy things until you reach equilibrium. The point that I'm going to make though is that let's say that this is equilibrium. So let's pretend that equilibrium is 75% B's, 25% A's under these conditions. Once you've hit equilibrium, what happens is I have a certain number of A's. Apparently I have 2 A's and I have 6 B's. Once you reach equilibrium, the delta G for the reaction under these conditions is going to be 0. Because, like I said, way back when, at equilibrium, there's a chance that A will turn into B, but there's also a chance that B will turn back into A. So even though A might turn into a B and release some energy, there's also an equal chance that B is going to be back converted into A and use up that energy. So once you're at equilibrium, the delta G for your reaction is 0. And that's here, when you're at equilibrium, there's no overall change in the free energy because you have your high energy stuff turning into low energy stuff, but you also have the same number of low energy things turning into high energy things. So that means delta G is 0 at equilibrium, but just to drive this point home, over here when we had a test tube filled with all A's, we were not at equilibrium, and so the delta G would be less than 0 because a whole bunch of these A's are going to turn into lower energy B's. And you can think of a different kind of reaction. Here's another pretend reaction. Molecule D turns into molecule E and vice versa, but this time D has low free energy, E has more free energy. You are going to have to pump some extra energy into D in order to turn it into E. But if you wanted to measure the delta G of this forward reaction, it would be equal to the free energy of E, because that's the stuff we end up with, minus the free energy of D. And we can tell that this is going to be a big number. This is going to be a smaller number. If you take a big number and subtract away a smaller number, you're going to end up with a positive. So in this kind of reaction, delta G for the forward reaction will be positive. And what you say when the delta G for your reaction is positive is the reaction is non-spontaneous. That basically means you're going to have to, for this reaction to go forward, it's going to have to get some extra energy from somewhere. So I want you to know this as well. I want you to know what a non-spontaneous reaction is, what a spontaneous reaction is. You should know what the units for delta G are. Okay, here come the equations that I'm going to drop on you. Here's the first one. There's an equation that lets you figure out delta G if you know the reaction quotient, or vice versa, right? You can, as long as you're only missing one piece in the equation, you can figure out the other one from algebra. And here it is. We're not going to go over where it came from. But the change in free energy of the reaction is equal to this weird thing, which just looks like another change in free energy, but it's not quite. It's called the standard change in free energy. That little zero-looking thing means standard free energy, plus R. R is the gas constant, which we've already seen before, so this is just some special number that you can look up, times the temperature. The T stands for temperature, and it has to be in units of Kelvin, times the natural logarithm of the reaction quotient. So if you want to figure out what the change in free energy is for a reaction at any particular time that's measured with Q, you can shove it into this equation. So a couple things to talk about with this equation. Everybody's favorite natural logarithm is back. Who knew that you were going to see the natural logarithm this much in your life? R we've already talked about, so I'm not going to talk about it at all except to say that it's called the gas constant, and you can look up the number, or I would give you the number. This is a little bit weird. This is also a number that you're either going to have to look up, or if you had other information you could figure it out. Basically, this is called the standard change in free energy. So we know delta G just means change in free energy. The only difference here is the word standard and this little zero raised up as a superscript. Standard change in free energy is basically what the change in G is under a set of standard conditions that people have agreed on and have already made measurements on a lot of the time. And you don't really need to know this, but these are the standard conditions. If you have a gas in your reaction, the initial pressure of any gases is 0.1 megapascals. The initial concentration of all the materials, if they're dissolved in water, is 1 molar. The temperature is 25 degrees Celsius. If you're under these conditions, then you're under standard conditions. If you have a pretty common chemical reaction, chances are someone has already figured out this number under the standard conditions, and that means that you can use this equation. Right? You can look up this particular number in a book or on the internet. You can look this up on the internet. You'll be able to measure the temperature that your reaction takes place in. If you can figure out what Q is, then you can figure out what the change in free energy is for your reaction at the snapshot in time that Q was taken. So you either have to be told what the standard change in free energy is, or you have to figure it out from other information. And we'll do a sample problem or two in the next video. But one thing to point out is that you should know this equation or have it written down and ready for a quiz or a test. Now I want to talk about this equation and talk about something that we had mentioned a few slides back. So here's our equation. You're just going to have to sort of accept it on faith that it's correct. Remember, a couple of slides back we said when your reaction is at equilibrium, there's no more change in free energy. And again, what that means, also written a couple of slides back, is when your chemical reaction is at equilibrium, the change in free energy is 0. Well, we can shove a 0 into this equation. And since we're at equilibrium, we can shove a KEQ into here, because KEQ is just a special case of Q when we are at equilibrium. If we do that, well, we put a 0 here, and we're going to put a KEQ here. Now we've put the KEQ in. You can use algebra, right? We can use algebra, and we can get this and this on opposite sides of the equal sign. We can do this by subtracting RT natural log KEQ from both sides of the equation. On the right side, they will go away, and what that means is another equation, and here it is. If you want to figure out the standard change in free energy for your chemical reaction, all you have to do is figure out what temperature the reaction took place in and figure out what the equilibrium constant is and plug it into this equation. So the standard change in free energy is going to equal -1 times the gas constant times the temperature in Kelvin that the reaction took place in times the natural logarithm of the equilibrium constant for your reaction under those conditions. So this is the way that most people use to measure the standard change in free energy for a chemical reaction. And you should have this equation ready as well. This equation down here is just a special version of this equation up here. It's just the version of this equation when we are at equilibrium, but it will be useful as well. So that is the end of this video. The next video and the last one for this week is going to be a couple of sample problems, or one sample problem with 2 parts.
Fee, fee, fi, fi, fo, fo, fum. I smell smoke in the auditorium. Charlie Brown, he's a clown. That Charlie Brown, he's gonna get down. Just you wait and see. Why is everybody always picking on me?